Hi everybody, my name is Dankovich. I'm from here at the University of Maryland, and I'm here to talk to you guys today about human-machine interfaces. So, we're going to briefly discuss a little bit about why I'm interested in this, what is out there already, and how what I'm doing is different and how it works. Then we're going to go over one finished study in static gesture recognition, and one in-progress study in doing gesture recognition on subjects who have some motion at the same time. So the motivation is real simple. People are fragile. Can't speak for the rest of you, I'm accident prone. So are a lot of people. Maybe 1 in 6 adults in the US alone have mobility issues. About 185,000 of us per year will suffer amputations, mostly transradial, meaning right through the forearm. And as discussed by earlier presenters, there's going to be a good 800,000 strokes just this year. And that's the US alone. When you start to look at developing communities, the statistics grow a bit more grim. So, in theory, medical robotics change lives. I mean, that's why we're all here today, right? We want to make a better world with wearable robotics. And bioelectrically controlled prosthetics are incredibly powerful modern technology. Stroke rehabilitation gloves, like the Raphael glove pictured here, help people get their mobility back at a cost. $50,000 for most of us isn't something we have floating around in our pocket. And unfortunately, there's a distinct correlation between poverty and the likelihood of having traumatic injuries that reduce your mobility, cost you limbs, etc. Now, the research community has started to move into resolving that issue. The open source 3D printing community has started creating things like the Hero arm, which is a 3D printed arm that uses lower-end myoelectronics to control it. And, once again, feedback? Sorry, but. And the PIY glove, which is a 3D printed version of the Raphael glove in the last image. However, the interface reminds a common driver for cost, which drives the prices up for a lot of people. The standard EMG used in both research and prosthetics control is the Autobot 13E200. They come in at about $400 per electrode, and in general, you're looking at 2 to 8 electrodes to interface with a given medical device. For a lot of people, that's a non-starter if they happen to be without insurance in developing communities or live below the poverty line. Now, a lot of researchers have started to look into less expensive systems. The Thalmic Systems Myoband was a perfect example. While they're currently out of business, they were selling for $200 a device, which can produce 81 to 94% gesture accuracy. And even lower end, there's devices meant to be attached to Arduinos, which unfortunately I wasn't able to find good comparative papers for. And the majority of people I've read seem to relegate them mostly to home use as opposed to having serious potential. The real challenge of finding inexpensive EMG lies in the fact that it's almost too sensitive. By the time you've picked up the nerve signal, just a tiny little impulse, you pick up overhead lights, your cell phone, your car, everything in the area. Merely sweating over the course of the day is enough to cause signal drift, and motion artifacts are a common side effect. A lot of technologies have started rising to try and move into the lower cost replacements for EMG, and I'd like to discuss one which I'm working on now. The basic principle is something you're probably all carrying in your pockets right now. If you have a touchscreen phone, you've used capacitive sensing. You have a positively charged electrode, negative plate, and capacitance is simply a function of how far apart they are, how much surface area there is, and what the dielectric constant of the separation is. Now, normally you find these in rigid interfaces, but there's no reason you couldn't put this in something flexible. In my research, I've stuck it between 2 layers of fabric and then wrapped it around a human limb. Humans are great ground planes. We are really negative as a species. So, you get this wrapped around a limb, but you now have a cross-section of the limb. Like this handy little doodad here. This cross-section tells you exactly how much skin is in proximity to it, right here at this baseline position. Now, if you move, you need to flex and relax muscles for any motion you generate. That changes the quantity of skin in a given proximity, and as a result, changes up the capacitance. Now, one of these sensors isn't going to give you everything. I found 7 sensors is normally needed to give a reasonable prediction of gesture and motion. The total cost of this comes in at about $4.77 in parts and maybe $30 for electronics, making it suitable for lower end. But of course, the real question is, does it work? Cheap and non-functional? How to use this? The first study I'm going to discuss is one in which we looked at static motion. We had a fairly small number of participants in this preliminary study, and what we had them do was go through 32 different endpoints, and then we stream this data over to a computer via Bluetooth, process it offline, and now let's discuss more detail on it. We used a rig to ensure that their arm remained in a constant position, because early on we noticed that the bicep inserts under the brachial radialis, so if you bend your elbow, this changes the signal for several of the sensors. Future studies will look at whether you can pick up elbow motions as well, without losing integrity of the signal. A sliding stage is used to move objects into their range so they could grasp without moving the arm at all, which we then set them through this Kataski Taxonomy. This is a basic set of graphs that describes what you do on a daily basis, everything from picking up a coffee cup to killing a key in a lawn. It can be described by these graphs. We took them through some more fundamental motions, individual finger flex and extend, individual 3 degree of freedom wrist motions, to see whether we could detect those endpoints. And the results were yes. We used tenfold cross-analysis to predict performance outside of the data sets, to try and get a sense for how things would be in the real world, and ran them through 4 basic machine learning algorithms for categorization, of which random forest came in easily the best, at about 95.6% accuracy for most individuals we tested. We used confusion matrices to display what areas might exist for confusion and overlap in given subjects, because we want to get a better understanding for what might have gone wrong. In general, the results were pretty spot on, with the exception of subject 4. She was both the most slender and the shortest armed person in the group, which led to the 2 possibilities that it could have been body mass or arm length was a root cause. So now we're getting on to ongoing work. Unfortunately, I only got clearance to the IRB very recently to start testing, and all the data I'm going to be talking to you about in this section came from subjects I tested on 2 days ago. So it's a little bit new and fresh. Apologies if it's messy. Such as research. So for this, I tested on 7 different subjects, and we limited down the gestures to things that, after speaking to people in the prosthetics and rehabilitation community, they saw as fundamental things to get back. Things like picking something up between 2 fingers, grabbing with all of your fingers, or even just pointing the fingers to press buttons. We then had them rotate their arm between pronation and supination to see whether that actually can be picked up simultaneously to the gestures. We used an IMU to actually send data back to computers ground truth for the gestures, and then, again, processed offline. So you can see a more clear diagram of the gestures we used in this slide, along with the simple pronation and supination. The raw data, which hopefully is clear on the screen, gives you a sense for what happens as you roll through the gestures. There's definitely a distinct pattern of how much pressure is being applied to sensors, how close skin is, and we're able to predict with 9% average accuracy for users exactly what angle they were at relative to that neutral plane they started at, in terms of palm up, palm down. Now that's a great start, but could we predict grasps on top of that? Obviously, if you look at the data, a lot of it looks like it might overlap as they roll. The answer was kind of. On average, we got 80.6% gesture recognition, just using our basic users. The confusion matrix you see is actually for one of our less successful subjects in terms of this test, because I didn't want to just put up the best and give it a polish that it doesn't necessarily have. So it occurred that since we already have IMU data being fed, if we gave the angles input, we might achieve a bit more accuracy. As you can see, once we feed it the IMU data, giving it a sense of what the roll is, it boosts up the accuracy a little bit, but it also puts the errors into categories that have some degree of overlap. For example, the pinch and the squeeze motions are very similar in terms of how much muscle force is being used and in terms of the hand position. So this subtest also allowed me to look at some of my hunches from the last study. What I came up with was that body mass doesn't seem to have a big effect. I tested on people ranging from skinny to mildly obese without much pattern in terms of how accurate it was on these individuals. What really made a difference was the length of the forearm. If you look at the plot, you can see that above a certain forearm length, you started seeing results get right up around 90%, very accurate most of the time. However, below a certain length, it just dropped off and got really random. The hypothesis I'm going with is that the spacing of the actual sensors needs to be proportionate to the length of the arm used, because that way it falls closer to the bellies of the muscle. But that there's a somewhat broad range of medium, small, large, which I'll be testing as this study goes on. So in summary, for static testing, we were able to get 95.6% accuracy for 32 gestures. In dynamic motion, that drops by almost 20%. However, we're able to raise it back up a little bit by including the angle motion using an IMU. This comes in at about 2% of the cost of traditional EMG, and maybe 17% of the cost of the lower end EMG on the market. What we hope to do next is add another 60 people to this study so we can have some meaningful numbers. Test variation of sensor spacing on smaller subjects to see if that actually brings the accuracy back up. And do some direct breath force analysis for stroke patients and the like to see if we can help with modulating force output from hands. We're also currently working on machine learning training. Thank you all for your patience. Please ask me questions and make it feel useful. What you got?
Great talk, thank you. I had a question about the other devices, the conventional and the inexpensive. Did you test to see how well those patients performed with those other sensors and see how well your classification accuracy?
So that's, my basis for those has been looking at previously published papers and seeing what the ballpark figures are. A lot of So I tried to toss out the papers or purely open access journal or something where I could see an impact factor like 1.85, and then pulled a ballpark figure from the things that I considered more legitimate professional journals. There definitely will have to be a phase of testing those directly in competition, though it might be a bit challenging to track down a Phalmic Systems lab bracelet at the moment, given that it's gone out of business, so it's now gone up to like $400 per unit as opposed to $200 today. Yes?
That's a great idea. Do you have problems with stray capacitance and capacitive coupling? Maybe that could be a bigger problem so that various sensors are not independent.
So, in the earlier versions, I had significant problems with that because there was a much longer wire that I was using to connect them, which had flexibility to move. And it was also a much wider wire, which just produced visible variation. By shortening the wire and using something much narrower, that cut down the obvious, like, press one sensor, the other ones that the wire passes over, showing really visible signs. In a sense, the lack of sensitivity has been my benefit here.
I'm more interested in something that's related to this, which is the tactile sensation. How does tactile sensation, have you tried to input what the fingers or other parts of the hand would be feeling when you're moving your hand and integrating into your analytic system?
So you mean actually giving a haptic feedback loop from this? So at this point, I don't think I'm there yet. That's something that would be fun to do down the line, but I think right now, until I can prove this works with reasonable accuracy on a larger subject group, I don't want to try and use this as a part of a feedback loop because it just seems like it's premature to make a closed loop on a system after proof if you're kind of all standing alone.
But you intend to do that in the future?
In the future, I have a lot of interest in, I'm working with the kinesiology group among other groups to see if I can use this as a direct, giving people kind of haptic feedback depending on their force modulation to help rehabilitation with clot hand palsy. And a few other groups I've spoken with about using it in similar contexts.
Great, then let's thank our speaker.